We have next up David with the first talk. You'll have a second one in 2 slots from now, I think. Yep. So say a warm welcome to David, and you go ahead.
Hi. So I'm going to talk about modeling digital signal processing. This is really a continuation for a talk I did last year at ORConf in Sweden, ORConf 2024. So this is a continuation where I talk more about the extracting frequency response and performance. And there's a GitHub repository there. So in summary, I'm going to give a very brief background to the kind of work this is involved with. But for more detail, ORConf 2024. And talk about the major new stuff, which is really being able to do frequency responses for linear systems, and then being able to simulate those in the time domain, and then extract the frequency response from the time domain, and working out signal-to-noise ratios and stuff like that. My main example is going to be a low-pass filter constructed from 2 parallel all-pass filters. I've got a few other examples which I'll probably just skim through. So just high level, what's the problem I'm trying to solve here? Is we're trying to integrate some sort of digital signal processing. If you're not doing it the way I do it, you probably run to MATLAB and Simulink, and you draw up a block diagram of your signal processing, and then you stick some signals in at the input, and you measure some outputs, and you try and work out whether the system's going to do what you want it to do. The stuff I'm talking about is all text-based. It's not graphical, but I think it works a lot better than this solution, and it's free and open source. So in my world, to define a DSP block, you define a data structure. It may be empty, or it may have a few parameters in it, independent of the input sequence. You define a function that returns an output sample as a function of the input sequence and the state variable. And that function may request 0, 1 or more samples from the input, so that allows it to support different sample rates. So you can support decimators, interpolators, asynchronous sample rate converters. But the vast majority of the time, it's 1 sample in, 1 sample out. And I described this in more detail in ORConf. There's a few other functions that you need to define, like the length. There's a function, the length of the input and the output type. It's all defined without a specific input sequence in mind. So the idea there is you define your system independent of your input, and then you can run lots of different inputs on the system. So what I'm calling a sample processor is a special case where it's 1 sample in, 1 sample out. And this makes a common case simpler. And in the past, I've coded this kind of helper, if you like. But it also actually enables, more importantly, it enables you to compose different circuit topologies. So in the past, the way I presented at ORConf, you've got a bunch of processors in sequence, so you can compose them. But you couldn't do things like fan out or have feedback loops, because there's all sorts of weird corner cases to do with sample rates and things, which just disappear if you guarantee one output for every input. So it just makes everything easier to define and more flexible. So previously, the only thing you could do with these processors is basically you could compose them to create a filter chain. So you're composing processors to make a bigger processor, and ultimately you want to apply that. You apply an iterator containing, describing the input to generate an overall iterator, which allows you to pull output samples out. Now I've added the capability of asking for the frequency response. So there's an extra function that you have to define, which basically, what is the frequency response of this one block, and then by composition and arithmetic of adding these things, you can basically define all sorts of linear systems. Transfer functions really only apply for linear systems, so I've got a small library of building blocks, and really, in general, like most of the time, you don't need to write your own response function. It's already there because you're composing out things. So the library functions already exist. And the really nice thing about this is you can define your sequence of filters or whatever, and up samples and down samples, interpolators, and all the rest of it. And you can then get the frequency response of it. Same description. You can stick samples in, get samples out, and run it in the time domain. And then you can compare the two, which is kind of like the whole point about this presentation. So as my example, I'm going to talk about, this is an old paper, but it's a really good paper. And basically, it's describing ways of designing really efficient filters, high pass, low pass, with special properties ideally suited for interpolation decimation. And so we're going to implement a fifth order IIR filter. The details here are not important. It's just a really nice example that I've chosen. And it consists of a parallel connection of two all-pass filters. And there's some special properties as a result of that. And I'm going to show loads of code coming up. It's all in one file, about less than 200 lines. The vast majority of it is like, to plot commands, but just pretty graphs. So on the bottom right there, that's the structure of the all pass. And then the top, that's the low pass, with two all passes in parallel, with one with an extra delay. So we're going to define the all pass transfer function, define the low pass structurally as two all pass filters in parallel. We're going to plot the transfer function, and we're going to then make a fixed point version of the all pass filter in a two-step process, starting with the floating point one and then moving on to the fixed point. We're going to simulate the fixed point, and then we're going to compare. So transfer function responses. This is all the code to go from the coefficients which are in that paper. So they're duplicated here in Julia. IIR is a library function I've got for just like IIR filter. So here are the coefficients, numerator, denominator, defining the all pass filter. Here I define the low pass as being two all passes in parallel, one of them with an extra delay and a scaling factor. I define like a bunch of points to measure the frequency over, and then this function freq_z dB calculates the frequency response at each of the points in the frequency array of that low pass. So that's 3 lines effectively to get the frequency response. Then we plot it, and we get the low pass filter transfer function. So that's pretty cool. But very briefly, you then start playing with this. Like in this case, I've got a little for loop set up to quantize this to the coefficients to certain to different precisions, and then recreate the low pass, plot the frequency response. So you can see different frequency responses as a result of the quantization of the coefficients. We can run these transfer functions at different sample rates. So here I'm running like the same one low pass filter at 3 different sample rates, the area sample rates, and then I'm now running like 1 low pass and then 2 low passes and 3 low passes, and getting the composite response. This is just to demonstrate that the transfer function stuff can work for multi-rate systems, and that's what these filters are really designed for: interpolation decimation filters. Going back to just a single filter, it was a low pass. If you zoom in on the passband, you see that there is ripple there. It's extremely tiny. It's a consequence of the structure. You can read the paper to read all about it, but this is in dB. So we're down in tens of micro dB, like ripple. I don't know, it's parts of a million, roughly speaking. It's saying we'll come back to this later. So now we're going to try and run things in the time domain. Now, the low-pass filter, as I just described it, you could run in the time domain. That wouldn't be very interesting. We're going to convert it into a fixed point implementation, so we can see numerical precision effects. So the first stage is to write our own floating point version. So here's the structure I talked about earlier. This contains the coefficient. Here's the processing function, which basically like, what block is it? What's the input? What's the state? The default value of the state is 0. And it's a function that returns the output and the next state. And then this is like a one-liner thing to tell it what the output type is. Switching to fixed point, it's basically the same thing, but there's a few extra bits been added in to make it fixed point. And fixed point arithmetic, you end up with extra LSBs, extra MSBs. You need to get rid of those to close the loop. So truncating things, clamping things, and just a little bit of annotation of some of the fixed point numbers. And then we will then stick a sine wave through this, and we'll end up with like a noisy sine wave coming out. And then we want to measure like how much sine wave is in there, what's the amplitude of that sine wave, and what's the noise underneath from what these quantization effects, and both at the input quantization and then the quantization inside the filter. So the way I do this is based on this paper. It's like an old paper, kind of old too. But really it's standard least squares. The standard undergraduate math, like linear matrix algebra stuff. There's nothing really special. The paper's a good introduction because it puts it in the context of signal processing. And I guess the one thing that I've done that isn't in that paper that I argue is kind of important is I use weighted least squares, which is a standard thing. And the weight applied is it's kind of like a filter. It's exactly the same as a filter, actually. A window. When you do an FFT, you apply a window. The weighted weight function's a window, and this has better properties. So how do you actually use this? So we're in the time domain now. We're generating a sinusoid, sticking it through an A to D. That was designed, specified in a one-liner as just rounding to a fixed point number. Pass it through the low-pass filter. Take a bunch of samples, collect them all up. Run the least squares algorithm, looking for a particular frequency, the input signal frequency, and this will return back like the magnitude of the DC component, the magnitude of that signal frequency. It will then subtract off the sine wave, like an ideal floating point sine wave from that, the output of the the noisy output of the filter to give you a sort of residual signal. And then we'll take a look in the frequency domain of the output of the filter and the residual signal, and we'll see like how they compare. And then we'll plot all that, and we end up with this. Now this is like a beautiful harmonic series because like my input frequency is such that the points are repeating every 100 cycles. So even though I'm running this thing for 16,000 cycles, it's really repeating every 100 cycles. So it's like a Fourier series. And as an example of something that's probably not a realistic way to be running this. If you run it at a slightly different frequency, or you add in more random noise, you can end up with more like this kind of more probably what you were expecting to see. Where you have the input signal, a nice perfect sine wave, and a noise floor. And the noise floor has a shape to it, and we can measure like the how much noise there is, work out signal noise ratio and all that kind of stuff. We can zoom in here, and I find this is just absolutely amazing. This is the mathematics of linear algebra. Like the FFT of the input signal or the output of the filter, is an impulse basically. This is the sine wave. We subtract off that sine wave. We're left with just the quantization noise, and the two plots that are on top of each other, apart from at the point with the signal, you can actually see the noise underneath the signal here. I think that's just amazing. It's like it's nothing to do with me. That's the math. So that was a single frequency, a single sine wave frequency. Stick the whole thing in a for loop. Grab the magnitude of the output, maybe the noise as well, and start plotting. And we reproduce the transfer function. Now, there's actually two lines on top of each other here. One is the measured, and one was from the transfer function. But you have to take my word for it. Like, like I'm not cheating here. And these are just showing the in-band and wideband noise, which is like just showing that it's independent of the input frequency, which is kind of what you'd hope for. So, okay, if we zoom in, this is like, to me, kind of amazing. Down at the parts of the million level, they match. I've got some other examples here. First order sigma delta. This is an example of sweeping DC. This is an example of sweeping AC signal level. CIC filter here, which, it's a lot like I discussed at ORConf. Block-based processing, overlap add, overlap save type stuff. So it's really quite flexible setup. So there's a simple framework. I've added the frequency domain analysis. I've added the performance metrics. It's all implemented in Julia. There are very few dependencies. You could implement it in other languages, but I would argue that you should consider using Julia whenever you consider using MATLAB. Julia is good for technical signal computing. And that's me. Thank you.
Thanks very much, David. Okay, question time from the audience. Okay, Ethan.
Yeah, thanks for the talk. Could you explain again, so does this compile into like Verilog in the end, like similar to like Simulink?
No. I mean, maybe at some point I will, I have in the past actually done things like that. But no, this does not. This is for just purely like upfront modeling. I explained that in the ORConf talk. But yes, in some ways it's a kind of obvious next step is to make this so that you can do that transformation directly.
What about an intermediate step like compiling down to, say, embedded DSP processors or something? I
mean, in some ways, if you want to output C code, it's the same as outputting Verilog. So that would be one option. If you want to like use the whole Julia infrastructure to generate a compile, and Julia's not so great at that. They've been adding and like to actually embed that object code. It's probably a step too far. So I think you'd probably want to convert to C. Yeah. In which case, it's much the same as converting to Verilog.
Okay, any other questions for David? No, okay, let's leave it there. Thanks, David.
Cool, thank you.